Hello, Algebra 1 students, and welcome to your last lesson in Topic 9. I think compared to our factoring and Topic 8 lessons, which were 11 lessons long, these 6 lessons hopefully fly by. Today we're not really doing much new. We're really just trying to bring everything together and make sure that you keep up with your practice from previous units as well as our current one. We are going to be comparing methods to graph quadratics, and as a nice little bonus at the end, we'll remind you of some of the other graphs that you should be proficient with at this point in your math careers. So let's get to it. There are 4 equations on the opener, and your job is to graph each one. All right. So why don't you go ahead and get started and do your best to show any work necessary, get everything on there, and then we'll chat. Ready, set, go. Okay. So you're back, and let's go ahead and take a look at the 4 equations generally first, and then we can go through, and we're actually going to compare the graphs on this page to our second page. I'm going to skip to the second page in a second, but the first thing that we need to realize is that there are 4 equations here, of course, and 3 of the 4 equations are quadratic. One of the more obvious quadratic equations has that x squared right here. So we know that one's quadratic, and if they're quadratic, we also know that their graph is going to be a parabola, that U-shaped graph. We should also recognize this x squared here, that's also quadratic. And we should recognize this equation all the way back from topic 7. That's our HK form that's quadratic. And last but not least, even though it's a little bit more hidden, we should recognize this first equation as quadratic. We've spent several lessons on it in topic 9. This is in our intercept form, and we know if we were to multiply all of this out using the box, there'd be an x squared. There'd actually be a negative x squared. But then what's our fourth one? Well, our fourth one is a blast from the past. We have these nice bars here. We say that those bars are absolute value, and the absolute value is applied to, well, if there wasn't absolute value, this would be a linear equation. There's no squared here. So this is linear absolute value. And spelling apparently is not my forte today. Awkward. There we go. All right, so let's just start right at the beginning, and we're going to discuss the different types of quadratic equations. There are 3 forms you need to be fluent or proficient with, and they're all on this page. So we're actually going to go to the second page and start summarizing these forms, and then as we figure things out, we'll kind of go back and forth between the pages. All right, 3 common ways to see quadratic equations. The first is in vertex form, which sometimes we call HK form. And the general equation for vertex form is that y equals ax minus h squared plus k. This is the form that we learned in topic 7, so if you need to go back to any of those lessons, please do. The second way you see quadratics presented is in intercept form. And for that one, we saw that ax minus q times x minus p, or p and q, whichever way you want to put those. And we spent a few lessons on it this unit. Last but not least, we see a quadratic in standard form. And that's what our last lesson was on, that ax squared plus bx plus c. We'd argue that there are probably 4 main components to a parabola. Those main components are the y-intercept, the x-intercepts, the vertex, and if the parabola opens up or down. I would also say that with the vertex comes the axis of symmetry, and we'll touch on that as we go through in just a second. So we're going to use the graphs on this paper to fill in how you would find each required component below. And then we're going to rank how easy it is to find that component, with 1 being easy and 5 being pretty darn challenging. Now, what we're going to ask you to do on this page is, even if you don't particularly find it challenging, the 1 should be the easiest relative to everything on this page, and the 5 should be the trickiest relative to everything. So even if all of this is easy for you, I think you can still probably present an argument that some of these components take more work or are a little more challenging than the others. So there probably should be a couple 5s on here, probably should be a couple 1s. That means, though, that we're not going to fill in the difficulty rating till the end of doing all 3 of these, because otherwise you won't know, relative to the others, which one is harder and which one's easier. So let's begin. Given an equation in f of x equals ax minus h squared plus k, which is called vertex or HK form, how do you find each of those? Well, let's go back to our vertex or HK form. Which one is that? Oh, that's going to be the second one right here, and let's actually try to find those, right? The y-intercept, we should be pretty good with at this point because the y-intercept, no matter what form, is always the same. So we know for the y-intercept, we just replace the x's with 0, okay, square it, minus 8. Now, because this is going to be our y-intercept and there's no variables here, we could use our calculator to do all of that math. I'm going to follow PEMDAS, though, just to keep our good math skills fresh in our brain. So I did what was in the parentheses first. Then we do the exponent next. A common mistake is people will multiply before an exponent, but PEMDAS, right? We need to go through and do exponents before multiplication and division. So negative 2 squared is positive 4. Then we multiply, and then we add and subtract. So our input was 0. Our output was 0. That means the y-intercept is 0. Easy enough. Okay. Next up, we need to find the x-intercepts. However, before we do that, let's take a quick second and fill in what we did down here. Right? To find the y-intercept, you replace x with 0 and use PEMDAS to find y. And that's going to give us a point, 0, comma, something. All right, x-intercepts. Well, the x-intercepts are found the same way every time as well. You need to replace the y with 0, or in this case, the output, because remember, g of x is the same as y. So I'm going to need probably all this space here, so I'm going to kind of be going down and up and just using a bunch of arrows, so you might want to write a little small. So we have this 2x minus 2 squared minus 8. Okay. And then as we go through, we would want to probably add our 8 to both sides, right? We're, again, because there's only a single x throughout this problem, this is a really nice way to go through and use SADMAP. We use SADMAP to isolate a variable to move all the numbers over to the other side. So I'm going to go through and start by adding 8 because that is our addition and subtraction. Remember, we can't do anything with the 2 in here because it's trapped by the parentheses and we haven't gotten there yet. So we add the 8 and that's going to give me 8 equals 2 times x minus 2 squared. Then we're on to multiplication and division, and I do see a 2 that's multiplying here, so I'm going to divide off the 2 that's out front. And this is going to give us 4 equals x minus 2 squared. Now again, I know the subtracting 2 is tempting, but it's locked in by the parentheses. Can't do anything till the parentheses are gone. And I think the only thing we can get to is the exponent. We took care of multiplication and division. To undo an exponent, we have to introduce that square root. And we know whenever we introduce a square root at this point, we need a plus minus. So square root of 4 plus minus 2 equals, now we don't need the parentheses anymore. There's nothing on the outside locking them in. And so we're here. All right, we've taken care of the exponent. We've gotten rid of the parentheses, so now we start again. Now we can get back to that addition and subtraction. How exciting. Okay. When we do this, 2 cannot combine with the plus minus. Right? This positive 2 that I have here needs to sit in front of the plus minus because we don't know if it's 2 plus 2 or 2 minus 2. And, of course, it is both. So we have x equals 2 plus 2. That's 4. And we also have x equals 2 minus 2, which is 0. So 2 x-intercepts, 4 and 0. Let's summarize that quickly. There's quite a lot of work there. We're going to have to remember that, I think, right? So our x-intercepts, we had to replace y with 0. And I'm using that w/ for with. Then SADMAP to isolate x. And that will give me something, comma, 0. And actually, often with parabolas, we'll get a couple answers here. So we have something, comma, 0, and something, comma, 0. And it should make sense that we probably get 2 answers, right? Because eventually this is going to be that U-shaped graph, and our U-shaped graphs usually cross the x-axis, right, twice. So we should get 2 answers there. All right, whew, we've been doing a bunch of work. Let's find the vertex. Oh, I think the vertex is easy. This is in vertex form, right? Isn't our vertex already given to us? Opposite of h, positive 2, comma, negative 8. 2, negative 8. Look at that. Nothing to it. So how did we find the vertex? Well, the vertex here was just h, comma, k. And I'm just going to make you a reminder, this is the opposite, right? And so we just got that from there. Easy. Okay, and then last but not least, which way is this parabola going to go? Well, we know that by, I think, looking at the a value that's out front. This a value is a positive 2, and in fact, we can use that a value to go up 2 over 1 from the vertex to get 2 more points. We also know, because a is positive, that our graph is going to be opening up. I'm even going to sketch in this parabola here, like so. All right, so just a reminder, which way does the parabola face? You need to look at a. If a is greater than 0, that means a is positive, then our parabola goes up. If a is less than 0, so if a is negative, then the parabola goes down, right? We can see that a over here. All right. Last but not least, we should probably finish off the domain and range. Actually, let's save that for the very end, since that's not one of our components. We'll do all of the domain and ranges at the same time. Okay, so we have our vertex form done. Nothing too terrible, though those x-intercepts are a lot of work. I think out of vertex form, the x-intercepts definitely take the longest amount of time. Let's jump into our next one of 3, though. Given an equation in, what is this form called again? Oh yeah, this is our intercept form, sometimes called factored form, right? How do you find each of these? Well, let's find our equation in intercept form. Where are those parentheses? Here they are. And we'll start with the y-intercept. I'll try to keep my colors the same. We used green. So the y-intercept, I think this is the same idea, right? F of 0 equals negative 0 minus 1 times 0 plus 3. Again, you could use your calculator here, or we could just use PEMDAS. I'll do what's inside the parentheses first. And then we multiply. Negative times negative 1 is positive 1. And then 1 times 3 is 3. One of those really common questions I get is, do I distribute the negative to both? And the answer is no. You only distribute if there's addition and subtraction. All right, so we end up with a y-intercept of 3 here, so we should probably put that on the graph. All right, so how did we find the y-intercept? Well, I think it's pretty much the same thing we did up above, right? So you replace x with 0, and you use PEMDAS. And I'm going to add or a calculator. Because calculators are real nice for the y-intercept to find y. So this gives us, again, 0, comma something. All right, let's tackle those x-intercepts, and you might be feeling a little apprehensive because of how much work we had to do over here, but I think for these x-intercepts, because this is an intercept form, it's probably a little easier, right? We start off by just setting f of x to 0. So 0 equals negative x minus 1 times x plus 3. Once we're here, we're in factored form, and we're not going to use SADMAP. There's more than one x. That's the giveaway. We're not using SADMAP. You can't combine those together. So we just follow our zero product property, right? We have 2 factors. I'm going to leave the parentheses off. We have, oh, and I switched it. That's all right. We have x minus 1 equal to 0, or x plus 3 equal to 0. We take our 2 factors, and then hopefully we can do some mental math, right? We undo subtracting 1 by adding, so we get positive 1, and we subtract 3 from both sides to end up with negative 3. Let's get these on here. We have positive 1 and negative 3. Okay, so I think there was quite a bit less work for these x-intercepts than there were for the others. So let's go ahead and summarize what we did, though. To find the x-intercepts, right, we still replace y with 0. But then we're going to use that zero product property. I meant to put, there we go, property to make 2 equations, I abbreviated equations, equal to 0, right? And then we have SADMAP to solve. And so we end up with, again, those two answers, right? Something comma 0 and something comma 0. All right, let's get to the vertex. This vertex shouldn't be too much of a surprise. It's the one that does have a little bit more work here, but we've done this a few times now, so it's not going to be a huge shock, especially since it should be fresh in our minds. Our vertex is, of course, going to be h comma k. The h value, though, we know always occurs, or the vertex always occurs exactly in between the two x-intercepts. So 1, 2, 1, 2. It looks like exactly in between is negative 1. The k value, though, we don't know where this is going to go. We can cheat a little bit, and we know the negative means my parabola is going to go down. So it's got to be somewhere higher than 3, right? It couldn't be at 3. That would be a non-symmetric parabola, so it's got to be somewhere up here. So how do we do that? Well, we take our equation that turns x's into y's. That's the only equation we have up here. And we replace x with negative 1. So I need to find f of negative 1, which is negative negative 1 minus 1, negative 1 plus 3. Now, I should have mentioned this up above, and I will mention it now. When you substitute something into the equation, you do need this negative here. However, you might have noticed that on my zero product property, I didn't use that negative at all. I didn't distribute or do anything. You can distribute the negative to one of these. There's nothing wrong with it. You'll get the exact same answer. However, the zero product property just cares about the actual factors. There's no x involved here, so it doesn't affect the answer. So you can leave it off for the x-intercepts or bring it if you're nervous. That's okay. However, the vertex, or when we found the y-intercept, you do need that negative. It's part of the problem. So we get negative 2 times positive 2. And hopefully we can see here that this becomes a positive 2. And then we get 2 times 2, which is positive 4. Negative 1, comma 4. Okay. So if we find the vertex, there are two pieces to it, right? Our vertex is, again, an hk. However, this hk is markedly harder to find because it wasn't given to us. So there's two things to do. The h is in the middle of the x-intercepts. And, of course, the k is, we're going to say, substitute h value in for x. All right, the last part is determining which direction the parabola faces, and it's really going to be the same thing that we did up above. I'm also just going to add in on here that the a value can give 2 more points from the vertex. Remember, we're usually trying to sketch 5 points in to give our parabola some decent accuracy. So if we go back here, let's try to do both things. Let's first figure out which way this parabola is opening. And if we look at our a value here, this a value is negative 1 that's hiding out front. So that negative means our parabola is going to open down. And if we wanted to use negative 1 over 1 from the vertex, we can go down 1 over 1 to get 1 point, but we can also go down 1 over 1 to get a second. And from here, I think we can sketch in that parabola with a decent amount of accuracy. We have the x-intercepts, the y-intercept, and we're looking just fine. All right, we have one to go, our last one here, so thanks for sticking it out. And then you guys will get a bunch of chance to practice, and that's, excuse me, that's the class for the day. So the last one is our most recent equation. This is an equation in standard form, right? We first really see standard form, even though they don't quite call it this, as like slope-intercept form, right? mx plus b at the end. So let's go ahead and apply that to everything else with quadratics. The first thing we're going to do is figure out that y-intercept. Now, of course, you could, I did this in green before, you could just go through, I said green, there we go, and replace the x's with 0. However, as we've seen over the last day or two, this is actually a bit of overkill. And the reason it's a bit of overkill is because the y-intercept is just the 8 that's at the end. That's pretty nice. If it's fortunate our graph goes up to 8 as well. All right, x-intercepts. Let's see what we can do. I think for our x-intercepts, the first step is always the same. We replace y with 0. So 0 equals, and then we still have that x squared plus 6x plus 8. Okay? But then, here's that issue. We have two different x's, so we can't use SADMAP. And the only way we really know at this point if we can't use SADMAP is we have to put this into factored form so we can use that zero product property. To get to factored form, you're probably going to want to use the box. And again, this is one of those where you should be able to do it without the box, but I'm writing box on here so that if you look back at your notes, you're like, oh yeah, we could use that box method. Right? All we need to do, though, because there's a 1 in front, which is very convenient, is just find two numbers that multiply to make 8 and add to make 6. I know we start with x and x. That's the only way to make x squared. And what multiplies to make 8 adds to make 6? It is going to be 4 and 2. I tend to use this one a lot. All right. Once we're here, now we're in intercept form, and I think the rest is pretty straightforward. Right? We need to go through and make two equations. We need to do x plus 2 equal to 0 or x plus 4 equal to 0. And then SADMAP to solve. Subtracting 2 from each side gives us an x of negative 2, x of negative 4, and we should be set. X is negative 2, x is negative 4. Excellent. Whew. Should probably fill those two in while I'm thinking about it. So as we jump back to this second page, we can start with our y-intercept. Just a reminder for the y-intercept, you can always replace x with 0. There's nothing wrong with that. But for standard form, we're just going to go through and say that the y-intercept is just c. So the y-intercept is c. Easy enough. So we get the point 0, comma, c. The x-intercepts had several steps, right? First, we had to replace or substitute x with 0. Okay. Then we had to use the box to factor. Okay. And then we had to use the zero product property to solve. A bunch of steps there. All right, let's go ahead and do the vertex. The vertex, I think, is going to be the same thing that we did before because, unfortunately, we can't see the vertex in this equation, so we probably want to build that HK. Now, I will give you a couple different ways you can do this. There's a faster way, but the slower way around is that we know the vertex is going to be something, comma, something. So we look at these two x-intercepts. We know it's exactly in between, and the number in between is negative 3. Now, I noticed they're only 1 apart from each other, so I bet I can actually tell you what the vertex is, right? It could be here, it could be here, it could be here, something like that. But we can use the a value to narrow this down. Since a is 1, I bet I can go down 1 over 1 in each direction and end up with the vertex, because that makes the slope work, up 1 over 1, right? So my guess is the vertex is negative 3, negative 1, but I can also double check that. And the way we double check is we substitute in negative 3 in for all of these x's. You might want to use your calculator. I'm definitely running out of room here, but it's nothing too terrible. Help me with it. This is 9 plus 8, that's 17, minus 18. And 17 minus 18 is indeed negative 1. Again, if you can use your knowledge of the a value to backtrack to get the slope or to get the vertex, good, that's great. Save yourself some time, right? If you find shortcuts, please, please, please feel free to use them. Just make sure that the shortcuts work each time. If you're not sure if they work, ask your teacher. All right, last but not least, we need to look at that a value, which we already said is 1. That only gives us an up 1 over 1, but as we'll touch on in just a second, I think there's an axis of symmetry that always runs through the vertex, doesn't it? This axis of symmetry is x equals negative 3, and we can do the same for the rest of these. This one would give us x equals 2, and of course this one would give us It goes through the x-axis, right? So x equals -1. And that axis of symmetry lets us reflect points to find one more. And I see that the y-intercept is 3 away on this side, so I can probably go out 1, 2, 3 and get the y-intercept on the other side. I think this probably gives us enough room to create a parabola. My computer cut out a little ways through, but that's okay. And we're good to go. All right, so let's finish summarizing that, and then we can get on to the rest of our practice. All right, so what did we do to find the vertex? Well, you had two options, and I'm really just going to be a bit lazy here, and I'm just going to draw an arrow up and say, same. But I'll write you a reminder, right? See if a value can help. And then last but not least, how do we know what direction the parabola faces? Well, we use the a value, right? If, whoops, kind of ran the u and the e together there. If a is positive, then we know the parabola goes up. And if a is negative, we know that the parabola goes down. Okay, so we have 4, 8, 12 different ways that we need, or methods we need to understand. Now, some of them are pretty much the same. But what I'd like you to do is to go through and consider the difficulty both when you compare side to side like this and top to bottom, and decide which ones are the easiest, in the middle, hardest. And you don't necessarily have to have one of every rating, but you should definitely have a 1 and definitely have a 5, and then the others probably fall somewhere in between. This is a little bit subjective. That means it's subject to your opinion. I don't think there's necessarily a right or wrong answer. But again, there's 12 of them, so rank them, and once you're done ranking, unpause, and we'll quickly chat. Ready, set, go. All right, so hopefully you went through and rated those. I'm not going to do them because, again, they're pretty much subject to your opinion, but some of them are pretty easy, right? Like the vertex, pretty darn easy. The y-intercept down here, pretty darn easy. More complicated ones, I'm sure the x-intercepts for vertex form are pretty complicated. X-intercepts for intercept form or standard form, pretty complicated. So either way, whatever sounds good to you. And then we're going to get some practice in. Now, practice-wise, we have 1, 2, 3, 4 quadratics on the third page, and you're going to have to identify the form and do the work to find all the components. The last page, though, is that in-class review, and we have 1, 2, 3, 4 equations here that you need to be pretty comfortable graphing. And we actually see this absolute value pop up again. So I'm going to demo that absolute value on the first page if you need it, and then we'll kind of go through and see if you need any help on the rest. So, absolute value-wise, there's a little bit you guys will need to remember. And again, if you want to start on the quadratics and come back and listen to this, that's totally fine. But here we go. First things first, the y-intercept is still found the exact same way. So when I find the y-intercept, we're just going to do h of 0, okay? 0.5 times the absolute value of 0 plus 1 minus 3. I'm just going to work to the right, and again, you'll find that many of your calculators obnoxiously don't have an absolute value button. We're working on that. Hopefully we'll get you some more updated ones from like this century. And so you'll have to be comfortable with what absolute value does. And can you remind me, what does absolute value do to any number? Right? We treat it like parentheses, so I did what's inside first. Well, absolute value measures how far away a number is from 0. It gives us the distance, and distance is always positive. So absolute value is always going to make whatever's inside positive. So the absolute value of 1 is just plain old 1. So I changed it to parentheses, and I applied the absolute value. Last but not least, we have 0.5 times 1. That's 1/2, or 0.5 minus 3. That's negative 2.5. You can check my math later on if you'd like. So, negative 2.5 on the y-axis. Doesn't have to be perfect. The x-intercepts, though, again, this blast from the past, might be pretty tricky for you, and I wouldn't blame you at all. Okay, so we set 0 equal to 0.5, absolute value, x plus 1, close that absolute value, minus 3. Now, we learned two different ways to do this. One with piecewise functions, and then the more common way, which involves isolating the absolute value. So let's do that first, right? If we think SADMAP, it's really the same rules as quadratics. There's only one x involved. So I think the first thing we can do is at least add 3 to both sides. Not a surprise. So we end up with 3 equals, and I'm going to change the 0.5, and you'll see why in a second, to 1/2. I almost always prefer having fractions instead of decimals when I'm isolating, and we're going to see that actually why right now. Because I took care of the addition and subtraction. I can't touch this because it's inside absolute value, which is a type of parentheses or grouping. So we need to undo this 1/2, which is multiplying out front. If it was still a 0.5, you might be tempted to say, oh, divide both sides by 0.5. And you're right, that will work. But many students have an issue doing 3 divided by a decimal. Now, because you can use your calculator, that's not too terrible. But I always like to make sure that you're comfortable doing this without a calculator. And so the better way, I think, to do this, to get rid of this fraction, is just to multiply by the reciprocal. We've learned that reciprocals always cross-reduce, nothing too bad. And so if I multiply one side by 2 over 1, I need to multiply the other side by 2 over 1. But 2 over 1 is just the same thing as 2, so let's just keep it there and see what we get. 2 times 3 gets us 6, equals the absolute value of x plus 1. All right, we have successfully gone through and isolated the absolute value. Now, why was that useful for us? Well, we need to remember what absolute value does. In particular, if this inside piece right here, if x plus 1, if we found the right x to make that equal to positive 6, then what would the absolute value do to positive 6? Well, it would keep it as positive 6, and that would be okay. So if I'm able to solve this and find what makes the inside equal to positive 6, I think we're good. In fact, let's quickly solve this. If we subtract 1 from both sides, we get x equals 5. Can we check that? If we do 5 plus 1, you get 6. Then you do the absolute value, but the absolute value of 6 is still 6, so that works out just fine. However, we also need to realize that if the inside of this, if x plus 1 became negative 6, I think we'd still be okay. Because, and actually let's solve this first and then go from there. I'm going to subtract 1 from each side. That's going to give me negative 7. If I wanted to check this, right, we'd go through and we'd say negative 7 plus 1, that's negative 6. But then what does absolute value do to any negative? It makes it positive. So the trick for solving absolute value is to make two equations, one equal to a positive number, one equal to a negative. And this is actually pretty similar to our vertex form of quadratics, though there's no square root involved. Okay, so we can go through and graph these. Unfortunately, one of them is a bit off the page, but that's okay. I've got enough room over here, negative 5, negative 6, here's negative 7. Give or take, something like that. Doesn't have to be perfect. All right, so we took care of the x-intercepts. Let's find the vertex. Luckily, all of our linear absolute value equations, at least so far, are in vertex form. We know how to do vertex form. Let me switch over to that yellow again. Opposite of h, comma, k. Some students will say, well, absolute value makes everything positive, so the 1 still stays positive. It does not. HK form rules here. So we get negative 1 comma negative 3. And then we can actually get a few more points on here because I know that the slope is 1/2, right? 1/2 instead of 0.5. And absolute value of linear functions has a constant slope. I can go, starting from the vertex, up 1 and over 2. Up 1 over 2, up 1 over 2 the other direction. Up 1 over 2, up 1 over 2. We can see everything lines up very nicely to make our V-shaped linear absolute value function. Okay, I did promise you we'd go back through domain and range, so let's do it quickly. Domain we've talked about 500,000 times. We know the domain is going to be all real numbers. The fancy way to say all real numbers, or at least real numbers, is that double bar R, and I'm going to be pretty lazy here and put it each time. You can also say something like negative infinity to infinity, or you could go old school and just say all real numbers. All of those mean the same thing. You should be comfortable with all of them, except maybe that double bar R is maybe less common in Algebra 1. The range measures the outputs, or visually how tall your graph gets. My range here, the highest it gets is 4, and it goes down for the rest of the time. So we could say that the y's are less than or equal to 4. If you wanted your interval notation, then we go through and we say the lowest number comes first over here, and the lowest number, well, there is no lowest number. It gets infinitely low, and parentheses, because we can't be equal to that, and the highest it gets is 4. For me, if you just even wanted to write that in words, that's fine by me. All right, our second one looks like the lowest it gets is 8 and goes up from there. So y is greater than or equal to, negative 8, sorry. Or interval notation, the lowest it gets is negative 8. It can be equal to it, and it goes up forever, so it goes up infinitely far. It can't be equal to infinity, though. The last two. The lowest it gets is 3, and it goes up forever, so we could either say y is greater than or equal to 3, or we go from, that's negative 3 again. Whoops. Negative 3 up to infinity. And last but not least, this one over here, the lowest it gets is negative 1, so either of these will work. All right, hopefully you're feeling confident, so why don't you guys go ahead and try the last problems on the last 2 pages. When I go through it, I'm going to go through it much quicker than I did on the first couple, and I'll probably leave a few steps out, so if there's anywhere that I lose you, just let me know. But go ahead, get this done, and I'm excited to see your success. Okay, you're back. Let's get to it. So, y-intercept wise, we're going to need to find f of 0 here. Okay, when we do f of 0, we just have 0 is just going to turn this into negative 1, positive 3. Negative and a negative is a positive, so we just get 3. F of 0 is 3. Excellent. X-intercepts, we've done this before as well. We're really just going to take each of these and set them equal to 0, but I'll show what we're doing first. 0 equals negative x minus 1 times x plus 3. So that gives me x minus 1 equals 0, or x plus 3 equals 0. And so we end up with an x-intercept of 1, an x-intercept of negative 3. 1 and negative 3. All right, let's go ahead and find this vertex. Vertex-wise, we know it's exactly in between those two. And I think the number that is exactly in between those two is negative 1, so that's nice. And then we are just going to substitute that number in. I think you could actually even use their slope here. Realize that this is only 1 away. I bet it's going to be 4, but let's double check just in case. So we're going to find f of negative 1, which is negative 1 minus 1, negative 1 plus 3. Simplifying a bit, negative 2 by 2. And yep, I'm looking at it. This is positive 2 times 2, which will be positive 4. If you get a number that doesn't work out, or if you're not sure if it's right, put it on the graph. And if it's in some weird spot, like it's down here, I mean, that's clearly not going to make a parabola. You probably made a mistake somewhere. Just double check on your calculator. I think finishing this off, we can use the slope to go down 1 over 1 in each direction, as I thought from earlier. So we've got this 5th point, and we can get everything graphed. Looks pretty nice. Domain, all real numbers. Range, we're at 4 and below, so y is less than or equal to 4. So what did that one take? A minute versus the 15 minutes we spent on the last ones. Okay, here comes our next one. Okay, looks like HK form to me. I'm going to do the same thing that I did with the absolute value. I'm going to think of this as negative 1/2, because I imagine at some point we're going to have to solve, and that's going to help us with our a value, which is good to mention that we have this fraction here. So, y-intercept first, nothing new. G of 0, we have negative 1/2 of 0 minus 1 squared plus 2. Negative 1/2, that's negative 1 squared plus 2. Negative 1 squared is 1, and negative 1/2 times 1 is negative 1/2 plus 2. 2 minus 1/2 will give us 1.5. Tend to use decimals a little bit more when I graph, but for most of the math I do like the fractions. So I'm looking at a y-intercept of 1.5. We'll see if I made any mistakes later if that point doesn't work out. But let's find those x-intercepts. So x-intercept wise, we need to replace g of x with 0. You'll notice that I gave you a little bit more room here because these x-intercepts, as we saw before, take a little bit more time. We're going to go ahead and subtract 2 from both sides. So negative 2 equals negative 1/2 x minus 1 squared. And then we need to undo this negative 1/2 that's right here. And to do that, we multiply by the reciprocal. The reciprocal of negative 1/2 is negative 2 over 1. Negative 2 over 1 is just negative 2. This becomes positive 4 equals, these guys are gone, x minus 1 squared. All right, let's introduce a square root. when you introduce a square root, don't forget your plus minus. And I run out of room, so the plus minus square root of 4. The square root of 4 is 2. We don't write the square root now that we've applied it. And we have that x minus 1, no more parentheses. Okay. Next up, we have to add 1 to each side. And as we discussed before, we can't actually add 1 to 2, so it just stays right next to it. This will give us two x-intercepts. 1 plus 2 is 3. 1 minus 2 is negative 1. So we have 3 and negative 1. All right, now that we found the x-intercepts, we'll find the vertex. The vertex should be easy. This is just an hk form, right? We have the h and the k. So opposite of h, comma k, it's at 1, comma 2. 1, comma 2 is right there. And I think that looks pretty good. We can see the curvature of our graph. Let's complete one more point with the help of the axis of symmetry. Right, our axis of symmetry goes right through 1. And you can tell we're 1 away, so I think this will be our corresponding point. You could have also seen that with the a value. The a value was negative 1/2, and you might think, oh, that means go down 1 over 2. But clearly that point can't work, right? If I sketch in my parabola right now, we can see what has to happen. It looks like this. And that down 1 over 2 is a point that's not on your parabola. That's because our a value always works as being written over 1. It means go down 1/2 over 1. And if you go down, and I'll zoom in so you can see this, down 1/2 and over 1, then it does work out. You always need to make sure your a value is written over 1 if you want to use that to find another point. And there's more information on that back in topic 7 if you need it. All right, domain and range. Nothing too surprising here. Our domain, all real numbers. The range, the highest it gets is 2 and it goes below, so y is less than or equal to 2. Continuing on through, y-intercept. Well, this one is in standard form, so I know when I find the y-intercept, it's just the number at the end. Don't forget the negative, -6. That looks pretty good there. X-intercepts, this one is the one that definitely takes a while, but if we're good at our box method, we'll be okay. I'll put the 1 here. I think I can probably skip straight to factoring. We don't need a box because there's that 1 out front. X and x. What multiplies to make -6 but is 1 apart? It's got to be 3 and 2. And to get a negative, the larger sign matches the sign in the middle. And I think we're good. Again, you could use a box to get here. Nothing too bad. Now we have two equations. X plus 2 equals 0 or x minus 3 equals 0. And I bet you can start to see that we get -2 and +3. So -2, +3. I like it. All right, at this point we have to find out what's exactly in between, but kind of looking at it, it doesn't look like it comes out very nicely. Now I bet many of you can still figure this out. However, I'm going to go with our mathematical approach, and I'm going to find what is exactly in between those two. And the way we do it, of course, is by finding the mean, or the average, one of the averages of these numbers. So we're going to take our x-intercept, -2, this is to find the h. We're going to add the 3 to it, and then divide by the two numbers we're adding up. This gives me 1 divided by 2, which means that our h value is 0.5 or 1/2. All right, you might want your calculator for this part. The question I get asked sometimes is, where do we plug 0.5 into? Well, you can certainly plug 0.5 in here, and you'll get your right answer. However, you can also substitute it into your factored form if you would like. They're equal equations. And I think the math tends to be easier in a factored form, so I'm going to substitute 0.5 into my factored form here. Okay? 0.5 plus 2 gives me 2.5, and 0.5 minus 3 gives me -2.5. Now, be careful. You might think 2.5 times 2.5 is 5. It's not. 2.5 times 2 is 5. This one ends up being -6.25, I think, if you do the math, but you should double check me on that. I think 25 squared is 625. Move the decimal twice. Okay, so let's go ahead and plot this vertex. 0.5 means we're going to be just over on the x-axis right about here, in between 0 and 1, right? And then -6.25 means go down to -6, and then not to halfway down, but just a quarter of the way down, right about there. All right, that should allow us to see our axis of symmetry pretty nicely. I meant to do that in purple, but that's okay. Here's our axis of symmetry. And then once we've done that, we can see that this point is half away, so we can get another point on the other side. Once we're here, I think we should be all right with our parabola. Looking pretty good. Our domain, all real numbers. The lowest our parabola gets is the k value of the vertex, so greater than or equal to negative 6.25. All right, last quadratic, and then we get to those last ones that are a review, and they go a little bit faster. The last one for our quadratic is another standard form. So let's see if we can do this one a little bit quicker than before. The first thing we can do is we know the y-intercept is 7, so that's good. So we can go ahead to our graph and put a point right at 7, right about here. Lovely. The form, oh, I guess I missed the form on each of these, but I've mentioned them. Standard form for these two, right? And the top right was vertex and the top left was intercept. So whoops-a-daisies. Let's go ahead and do the x-intercepts. Okay, so for our x-intercepts here, we're going to go ahead and set 0 equal to the equation, x squared minus 4x plus 7. And we're going to change this into factored form using the box like we did before. X and x. We have to figure out what multiplies to make 7, adds to make negative 4. And that should be pretty easy because to get 7 here, there's only one way to do it. I think it's just 1 times 7. But how do we combine 1 and 7 to get negative 4? In fact, I don't think there is a way. In fact, looking at this, I'm not actually sure we're able to put this into factored form. And so I wanted to leave this problem here to kind of let it stay in your mind because we've called this unit graphing factorable quadratics. And that means then that if we have a quadratic in standard form, as long as we can factor it, we should be able to graph it. But what about the ones that we can't factor? Is there no graph for it? Well, I think there actually is a graph for this. And so we've definitely run into a bit of an issue. So how do we finish graphing this? Well, the answer is for now, we don't. Right? We don't have a good way to graph this. Now, you could go old school and you could plug in many different x values, find the y values, and graph all of those. But that's a little bit too tedious. So keep that in your mind, the fact that some of these equations we might not be able to put into factored form. And so what that means is we might need some more skills and techniques to finish graphing something like this. In fact, that is what our final unit, topic 10, is about, non-factorable quadratics. So we're not even going to finish this graph here, and instead we're just going to jump on to the last page, our review page, and see what you guys remember from earlier this semester and last semester and 7th grade. So let's do the types of functions first so I don't forget it this time. This equation, y equals 2x plus 3, looks a lot to me like y equals mx plus b. This is a linear function. It's just going to make that nice diagonal line. 2x minus 3y equals 6. We learned this last semester. This is also strangely called standard form, even though it doesn't quite fit. But this is also a linear function. Okay. The third one we've seen before. Third one has absolute value, so it is linear absolute value. There we go. Absolute value. And then our last one has x as an exponent, hence its name. This is exponential. And we learned all about those in topic 6. So let's see what you guys remember here. Okay, our first one, y equals mx plus b, asks us to find the x-intercept and the y-intercept. Now, full disclosure, you don't actually need these for mx plus b, right? So maybe I'll actually graph this first, and then we can go back and remind you of how to find each of those. So graph-wise, we, I think, just need the slope, which is certainly 2 over 1, right, up 2 to the right 1. And then we need a point to use the slope from. But this y-intercept, this is an mx plus b. The y-intercept here is just going to be 3. But I'll show you a way you can find that if you forget. We start at 3, though, and we go up 2 to the right 1, or down 2 to the left 1. And we end up with something like this. Here is my nice linear function. Right? That's probably about as efficient as you can go, but it is also probably one of the poorest lines I've drawn in a while. There we go. Okay. X-intercept, y-intercept. Well, visually you could see it from the graph, but what if you forgot how to graph slope-intercept form? Many of you will have. Well, x and y-intercepts are always found the exact same way for any equation ever. To find your x-intercept, right, we're going to need some x value here, but we just replace the y with 0. So 0 equals 2x plus 3. And let's go ahead and solve. Subtract our 3 from each side. That ends up with giving us negative 3 equals 2x. And then we divide both sides by 2. And when we do that, it shows us that the x-intercept is negative 3 halves, or negative 1.5. And can we see that on our graph? Yeah, I think that's that point right there, right? Negative 1.5. Our y-intercept, which is 3, we could also find by doing the same method we did on previous equations, where we know the y-intercept is going to be something comma the y, and it always has an x of 0. So we're just going to go through, replace the x with 0, and follow PEMDAS. 0 plus 3, and that is certainly 3. Okay, once you add those two, you could have connected them and seen the line. Domain and range. The domain measures how tall our graph is going to get. It looks like it goes up forever and down forever, so not so shockingly, our domain is still all real numbers. What about sorry, I misspoke too. The domain should be how wide the graph gets. It does go infinitely wide. The range is the height, and the graph does go infinitely up and down, so our range is also all real numbers. Remember, sometimes you see that written like so. Okay. All right, second one. For this equation, you have a few options. You could isolate y, but I think actually finding the x and y intercepts is pretty quick here. To find your x and y intercepts, we just do what we've done before. We're going to go ahead and replace y with 0, and we're going to replace x with 0. So 2x, negative 3 times 0 cancels, equals 6. Over here, 2 times 0 cancels, negative 3y equals 6. How do you isolate x? Well, we divide by 2 on both sides, and that tells us that the x-intercept will be at 3, or in particular, 3, 0. Same thing for the y. We divide off the negative 3 out front, and this will give us that y is negative 2, or when x was 0, y is negative 2. We can graph each of these. 3, 0, 0, negative 2 is down here. And I think that's actually enough to see the slope, because slope is just calculated by going rise over run. It looks like I'll go up 2 and run over 3. And we can continue that pattern by going down 2 to the left 3. And this should give us enough. 3 points is fine to make our nice line. Domain and range, same thing. Infinitely wide, infinitely tall. Last two. Linear absolute value. Okay, well, we just focused on this one earlier, so let's fill in the easy parts first. Slope is certainly 2 over 1. The vertex is pretty easy as well, and I should have left a spot there for it, but that's okay. We can do it down here. Our vertex, hk, opposite of h, comma k, negative 1, negative 2. Okay. And then our x-intercepts. Oof, this is the one that takes a little bit longer, but it's not too terrible. 0 equals 2 absolute value x plus 1 minus 2. We're going to add 2 to both sides first. So 2 equals 2 times x plus 1. That's a little hat there that I couldn't quite erase. There we go. We need to divide off the 2 that's out front. If you divide both sides by 2, that leaves us with 1. And now we have absolute value isolated. So let's make our two equations. Right? Our two equations will be x plus 1, the inside of the absolute value, equals positive 1. Or the inside of the absolute value could end up equaling negative 1, because the absolute value will turn both of these to positives. When we go through and solve, 1 minus 1 is 0, and negative 1 minus 1 is negative 2. So I have 2 of these. We have 0 and negative 2. From here, the rest isn't too bad. The y-intercept, same process as before. And by the way, you can already see this on the graph, but I'll show you that in just a second. We just follow PEMDAS, right? 0 plus 1 is 1. Absolute value of 1 is just 1. This is 2 minus 2, which is 0. But again, we could already see that because we already had a point on the y-axis. This is one of those weird times where the y and the x are the same. Let's use the slope to finish it off. Up 2 over 1, up 2 over 1. In fact, all we really needed here was the vertex, and we could have just used the slope to find the rest. We didn't even need the math, but the math is a nice reminder. And then we have our lovely linear absolute value graph. Domain, we get infinitely wide. The range, though, different. We are not infinitely tall here because the lowest we get is 2. We do go infinitely up, but we'd only go from 2 to infinity. Or you could say y is greater than or equal to 2. All right, last but not least, our exponential, topic 6. Oof, the toughie. Well, a couple things to remember about exponential equations. They are either going to grow or decay, and we'll discuss how to find that in just a second. They also are not going to have an x-intercept. And I'm going to replace this really quickly to show you why, and I'm going to erase this after because it's irrelevant for this. If I wanted the x-intercept, this is the part I'm going to erase, we'd of course replace the y with 0. Now 2 is multiplying by 1/2 to the x, so I can divide both sides by 2. That will give me 0 equals 1/2 to the x power. Now the way we've solved these in topic 6 is we basically asked ourselves 1/2 to what power is 0? But there's an issue. If you do 1/2 to the 0th power, anything to the 0th power is 1. So that didn't equal 0. So then you might be tempted to say, well, what about a positive number like 2? Well, 1/2 times itself is 1/4. I think it'll always be a positive number if you keep multiplying 1/2. If you take it to a negative exponent causes you to do the reciprocal and then keep the exponent positive. And 2 over 1 to the first is just itself, or 2. So if negative exponents make your fraction positive exponents make your fraction positive, and 0 gives us an answer of 1, which is still positive, what exponent can ever equal or cause this to equal 0? And the answer is there is not one. So we will not have an x-intercept here. All right, but we will, however, have a y-intercept. So our y-intercept is the same as before, 2 times 1/2 to the 0th, and we follow PEMDAS. Nothing to do in the parentheses, but there is an exponent. The exponent is only attached to the 1/2, and anything to the 0th power we know is 1. Then we do the multiplication to find that there is a y-intercept of 2. Now, before I do these last couple numbers, I wanted to remind you of growth and decay. The growth and decay of an exponential function tells us the shape. If you have something that is growth, you have two options here. Either it will grow above the x-axis, or it will grow below the x-axis. Those are both growth. If you have something that is decay, the decay, of course, will do the opposite. You can either decay to the x-axis above it, or decay to the x-axis from below. What makes something growth or decay? Well, that is the number that's being multiplied by itself over and over again. And that in this case is the 1/2. 1/2 to the x power means start at 2 and just multiply by 1/2 over and over and over and over again. Now, if you take half of a number for a long enough time, what's going to happen to that number every time you take half of it? Does it get bigger or smaller? Well, it gets smaller. That number decays. So it is decay, and if you remember a times b to the x, it is decay because b is less than 1. Right? If this number is smaller than 1, then you're taking half of something every time it's going to get smaller. So I know this is decay, and this y-intercept is above the x-axis, so I'm already pretty confident that my graph is going to look something like this. But we can be a little bit more accurate. And the way we do that is we just find a couple more points. Let's find f of -2. That'll be 2 times 1/2 to the -2nd. Right? I'm just replacing the x with -2 here. And then we just follow our order of operations. A negative will cause the reciprocal to occur. And then 2 squared is 4 times another 2 is 8. -2 comma 8 is on our graph. -2 comma 8 is up here. Let's try f of -1. 2 times 1/2 to the -1st. Negative exponent gives us the reciprocal with a positive exponent. 2 to the 1st is 2 times another 2 is 4. And so we have the point -1, 4. We're going to cause this graph to decay. It never quite gets to the x-axis. It kind of sits right above it. Should have maybe done a little bit better showing that. Something like that is, still don't like it. It's going to kind of ride right along top. That one's okay. And the reason I did that is for our domain and range. Our domain, this still gets infinitely wide, all real numbers. The range, though, the height, it definitely goes up infinitely far. But what's the lowest it gets? Well, notice it doesn't actually even get to 0, does it? It skims right above the x-axis. So we say the range is y is greater than 0, or you could say 0 to infinity, both parentheses, because we're not equal. So, thank you for this nice review of graphing equations. Key part of today, quadratics. The second page is so useful. Make sure, please, you study it because we do have our second to last test before the final coming up. Thank you for tuning in, and I'm excited to welcome you back to our last unit, graphing non-factorable quadratics. And we're going to learn a couple really neat tools, and that shall conclude Algebra 1 for us for the year. Keep up the great work.